So he already realized that subconsciously. He's more nervous pulling from the red than the blue one. And people who can, there are obviously people who can know consciously very fast, and they're called experts. Expert mean that you've studied the subject too much that it's no longer intuition, it's your experience. So the trick is to use people as our features instead of regular features. Like, for example, book and movies, instead of describing them by their normal features like publisher, studio, author, editor, and so on, we'd replace them by the users who bought the movie or rated the book. And now we can cross-compare between two different items. Say, so user number 4 and 5, I forgot to highlight 3. 3, 4, and 5 both saw the movie and bought the book. And if you have multiple items, now you can use set similarity measures to compare between them. So obviously, the larger the intersection, the closer the two items are. These are like totally overlapping two items. These are mutually exclusive. Though this is very similar, this is very unsimilar, and obviously there are a lot in between. When that was applied to the movie dataset, the Netflix dataset that was published in 2006, you can also apply. It doesn't have to be either 0 or 1. Obviously, the movies were rated from 1 to 5, so you can use something called matrix factorization to defactorize this matrix. So if my original matrix, the movie rating dataset, it's n by m, where n is the number of users and m is the number of movies, you can decompose it into a multiplication of two matrices, u and v, where u is n times k and v is k times m. This is the same. This is the previous slide, but pictorially. So if you visualize the multiplication of two matrices, this matrix is basically described each user with two features. Okay, and the second matrix describes each movie with two features. And if you visualize these two features, if you rate or rank, sort the movies based on, let's say, feature number 1 and feature number 2 and feature number 3, what you find out are these pseudo features that normal movies would be like the comediness of the movie, or the actionness of the movie, or the romance of the movie, or the thrillness of the movie. I won't go over each feature here, but it's been analyzed. So the first feature was good defeats evil versus talking and emotions, realism. The second feature was love and safety versus action, peace, and surprise. So if you look at the top movies in feature number 1, there would be love and safety. The bottom list would be action and peace. So action is, in a sense, the opposite of love and safety, and so on. So these are other features that have been analyzed. So the great thing about doing this is now you can compare movies or any items mathematically, because each movie is basically a wave, a list of numbers. So if I have a list of numbers like that, I can basically use my favorite similarity measure to measure, compare, let's say, the movie Braveheart to all the movies I have in the data set, and pull out the movie that is most similar and the movie that is the most dissimilar. So in this example, you can visually see from the pattern here that the Gladiator is very close to Braveheart. Whenever they share similar patterns. So in feature number 5, say the comediness of the movie, they're very negative, suppose. Say the action is, they were very high, and so on. You can also see the opposite. I said the most negatively correlated movie, which is this movie here. Also, you can see visually that whenever those features are high, these are low, and vice versa. And the most interesting feature for me personally, that not only that you can describe now items in terms of continuous numbers, and you can visualize them as patterns, Um, you can obviously visualize them and or plot them in 2 dimensions or 3 dimensions. But the great thing is that now the users and the movies share the same features. They belong in the same space. Remember, if I can go back just a couple of slides or maybe a few more. Um, I've just visualized ways based on these 2 features. I can still visualize the same users on the same plot using the same 2 features. So if I go back to this plot, uh, if you can imagine, blue dots are the movies and the red dots are the users. Now you can in the same diagram or plot that these, for example, users like these movies, and these movies were close to these users. This is an outlier cluster. There might be fans of I don't know, animations or foreign movies or whatever. So those might be foreign movies, and those might be like foreign movie lovers, and so on. So that's one power of doing feature extraction, relying on the user item interaction versus explicit attribute set by experts or manually by people. And the second advantage is that you can now cross-compare. When Netflix published the dataset in 2006, and I think the first prize was awarded 2009 or something, they were planning on doing a second challenge, but they were stopped by a lawsuit because users used the dataset to compare it with the IMDb movie, the Internet Movie Database um, users and their ratings, and they were able to find out the identity of the users in the Netflix challenge. So they were a lawsuit was filed against them, and Netflix canceled the second prize and settled the lawsuit. So you can see how powerful the method is. You people were able to find out who are the same users from totally different data sets or site. This is IMDb and this is Netflix. They have nothing in common, even though the user identities were anonymized in the Netflix dataset. Let's go to social network example now. I can do the same thing with a Twitter data set. Say you have these accounts and you know who follows who. So one here means that user 2 follows NASA, for example, and so one means user I follows account J. Okay, if you apply the same technique and visualize the first 2 dimensions, what you get is something like this. And I'm sorry, but this is my third time coming to KSU and presenting that maybe the same slide, but it's a great example of so many things. That's why I keep reusing it. So let's put it back into context uh, of our current talk. Okay, so it positioned each uh, account such that close accounts are close to each other and further accounts are further from each other. Obviously, you can see in a micro scale that sports-related accounts are here, science accounts are maybe over there, Harvard, Stanford, MIT. Football-related accounts are over there. Saudi scientific-related. I had to put myself in there. You saw that comment. I'm sorry, but it put me close to, for example, CAX, where I work, and the Saudi Computer Society, and here Saudi Scientific, and King Saud University, King Fahd University. So that's on a micro scale. On a macro scale, if you look at each main axis, I'm not sure. Do you guys see the mouse? I keep using the mouse to point. Could you just verify in the text or the chat? Um, Hello, do you hear me? Or should I go to the main chat? Okay, I was on the private chat with the IS department. Never mind. Okay, so if you go along this axis, for example, you go from um, very serious academic, scientific accounts to somewhat political, up to very, uh, that's why I keep calling them pseudo features. It's hard to label those features, but you can see this like the variance between messy and MIT is very wide. So if you go from uh, east to west, it goes from very local accounts, very Saudi local account, to very global, and people in the middle are somewhere in between, like Queen Rani, for example, um, former President Morsi and Al-Baradi, and so on. So we can visualize obviously up to 2 features, but we can do the same thing. We can sort each feature and look at the feature or the pseudo featureness of each additional feature. So the third feature might be like the comediness of the account. All of these are like comedy-related accounts in Twitter. Notice that if people who know this guy, Neil Tyson, he's a scientist, he's the director of the Hayden Planetarium, yet he has a great sense of humor, so it makes sense that he was ranked, he was number 2 actually. So anyway, so the second feature is like the footballness of the account. The fifth is the Saudi-ness of the account. The sixth is the Egyptian-ness of the account, and so on. To complement that with a text mining related example, if you use the famous form of representing sentences in NLP, this is called the bag of words representation, where each sentence is basically represented with the how many number of time did word I appeared in sentence J. For example, word number 2 appeared 2 times in the sentence. Word number 4 appeared 19 times in sentence number 4, and so on. If you apply the same technique and rank each feature, what you will find out is this. The first feature was the stop words in Arabic, in, ma, an, kalla, and the totally opposite to the stop words in Arabic were, I think those are stop words in French. This is the result of analyzing a collection of YouTube comments, so it varies in languages and slang and everything. And we haven't labeled them at all. So all of what I've just presented so far was unsupervised. We haven't told the computer what language, what slang, what nothing. We've just told the computer what appeared with who. So the second feature was the top, or like the footballness, if you will. And the total opposite was like words from like Egyptian slang. And the third was like the top was kitchen-related words, and the bottom were religious, and so on. So those, if you visualize each feature separately, we can zoom in into a word. So take the word computer, for example. Now the computer was described into 500 pseudo features. Okay. So the computer learned that the computer has 500 pseudo features. That's kind of recursive. So the machine learned that the word computer has these values, these pseudo feature values. If you look at the top feature, feature number 1, that was feature number 309. Now, if you sort all the words in the dictionary according to feature number 309, what you get is chips, semiconductors, computer, software, so on. The second highest feature in the word computer was feature number 176. And the top words in feature 176 was telephone, cellular, subscribers, mobile, wireless. So obviously this feature has to do with the telecommunicationness or the mobileness of the word computer. The third was appliance, textile, machinery, electronic, automobiles. The fourth was translated languages, English, language, Arabic. So even though language might not be the first feature that pop into your head once you see the word computer, but computer is used a lot in automatic machine translation and natural language processing, which we are obviously it's in the subtitle of this talk. So it's obvious why computer would be related. The fifth one was the automobile-ness of the word computer. Now we're starting to get pretty far, but not very far. So the fifth feature of the word computer was motor, Toyota, Honda, Nissan, Hyundai, so on. Let's zoom in into another word. Say, take the word Oxford. Oxford has these 500 features, 500 values. If you look at the top feature, feature number 1, you sort the words according to, it was feature number 17. What you get is graduate, secondary, elementary, school, graduate. So this is obvious. Oxford is the university. This is the schoolness of the word Oxford. Okay. The second top feature of the word Oxford was science, institute, philosophy, CAS and CAS. So I've Googled this. This is an acronym for Chinese Academy of Social Sciences. The third one is interesting. It's like Reuben, Butler, Cook, Hutton, Lord. Obviously, very British words. The fourth are name of places and cities in the UK. Southampton, Aston, and so on. The fifth, like the prestiginess of the word Oxford, like Nobel Prize, prizes, shrine, laureate, so on. So not only that I can describe each word with a set of pseudo features, I can even go further. I can like take these two words, Oxford and computer, and like combine them and take the average, and what you get is a pseudo word. Okay, so if you average these two numbers together, what you get is this. So now this pseudo word has high values in almost these two words combined. So it's high here and here. Whenever this is high almost. So to visualize this in 2D, say this is, I'll take the same plot. So this is an imaginary plot, by the way. It's not something real or generated. I've just plotted this randomly just for illustration purposes. So if each blue dot here is say a word, and each let's say triangle is a sentence. Okay, so here's the word Oxford and here's the word computer. The pseudo word that I've just created might be somewhere here. Okay, it might not be a real word. It could be whatever is in between computer and Oxford. I'll leave that to your imagination. But we can also extend that to the sentence level. These 500 features, we can map them. I won't go into the details, but this is preliminary results that I'm just able to produce by searching for sentences closest to this pseudo word. So this has Oxfordness quality and computerness quality to it. So the first result was Wash, graduate from Purdue University in the U.S. state of Indiana, has a doctorate in computer science. So it doesn't have the word Oxford in it. That's the key thing. It didn't search for the Oxford and its derivative or suburbs, or it searched for the university-ness of the sentence. So obviously here it's a sentence about a university and computer science. The second one was the computers will help. I'm sorry, I can't pronounce this. I've Googled it. This is a university in Uganda, but anyway. So in University A and B of Science and Technology to set up a computer lab, respectively, according to an agreement reached by the two sides. Okay. The third one was Nazif graduated from Cairo University in. This is a tag for number, so this could be like 2006 or 2007. This is like a pre-processing step where you just normalize each numbers with a tag. Anyway, so with a degree in engineering before later doing a master's in the master's there in electrical engineering and a doctorate in computers at Canada's McGill University. Again, Oxford was not here, but McGill is pretty prestigious university. Once you go to the third, I think you were starting to get further. A graduate of the Massachusetts Institute of Technology, MIT, with a master's degree in electrical engineering. Dr. Landis was awarded a doctorate in solid physics. Notice nor the word Oxford nor the word computer appeared here, but the overall featureness of the word Oxford and the word computer appeared. So we're, in a sense, searching by semantic or sentiments rather than by text form or structure. Um, so the same concept was used by Google recently. They published a way in how to automatically translate two languages using word vectorization, or representing words in a vector form. Basically, what I've just described, the pseudo features for each word. So they've done this to on two separate languages, Spanish and English. And here's a zoom in. I'm not sure if the screen is clear, but these are like the numbers 1, 2, 3, 4, 5, and here are the corresponding words in Spanish. You can obviously see they have almost similar structures. So if you have a map in a certain language and a map in another language, all you have to do is just find the right transportation and rotation and linear transformation to transform language A to language B. Okay, what they did was they only used a small dictionary from English to Spanish to map a subset of the words, and they can interpolate on the rest of the words. And they reached pretty accurate results, but this is a long way from the traditional machine translation techniques, where you have to translate hundreds of documents and have their corresponding translations. You can just analyze two languages independently and just use a subset to map. Another application, this time by Stanford University, the machine learning group at Stanford University, they've used it to parse sentences. So take this sentence, the cat sat on the mat, for example. Now just imagine that each word has been represented with two values, just two pseudo features. I won't go over the technicality or the how they did it, but I'll just explain quickly what they did. Basically, they tried to learn from the corpus what made sense or what didn't make sense statistically. So, for example, cat sat on is pretty rare in any corpus because it doesn't make sense independently or as a standalone phrase. So it sort of awards and punishes combinations. So if take each layer as a combination of the previous layer. So this combination is pretty rare, so these links will have lower values. On the mat might appear as a separate phrase, so more frequently than say cat sat on, but so these weights will have more values. And as you keep on doing this recursively and recursively, it learned how to parse this sentence. So obviously, it didn't know this is a prepositional phrase or this is a verb phrase, this is a noun phrase. This is obviously done after the fact, after they've looked at the results. So oh, this is a verb phrase, this is a noun phrase, this is a noun phrase, and so on. But it did learn that in unsupervised fashion. Not only that, now each node here has its own pseudo feature. So each phrase has its own pseudo feature on the same space. That's the great thing. So you can map phrases with sentences or sentences with words, and you can visualize them all in one analytical diagram. So here's another example, like a small crowd quietly enters the historic church. They were able, obviously, to parse it just like they parsed the previous sentence, but they were also able to use the same principle. Now, I won't say the exact same techniques to parse an image. So this image has like grass and people and building, and the building contains like a roof and so on. They haven't reached yet the level of describing the image with words, but it's it qualifies as a breakthrough to me. It's analyzing an image hierarchically in this fashion. It's might be even hard for a person to come up with such a thing, let alone a computer. So this almost concludes what I want to. What is feature extraction? And on how to do it, there are multiple ways. I've previously gave a tutorial on PCA, I think, in KSU and MDS. You can also use neural networks to do that. There are multiple techniques to achieve the same, basically. I don't think I have time in this session to go for the mathematics and the algorithms, but allow me to do a shameful self-promoting plug here and say you can go to my YouTube channel. I have a few lessons on some of those principal component analysis, for example, and I'm planning to do more. So if you're interested in learning the techniques, you can go to the channel, and there's a long, boring videos waiting for you. Okay, so what does that all mean? Previously, and whenever you try to open an account, say in Hotmail or whatever, they used to ask you a lot of questions: where you're from, your gender, your age group, your occupation, your hobbies, etc. Because they, understandably, because they want to analyze their users and do some statistics. But nowadays, if you go, but this is obviously deters users from registering most of the time. So the more the questions, the less likely you will have users signing up for your website. Nowadays, if you go to Twitter, for example, and sign up, all they require is just your name and email and a password. And the reason is because they're already applying. So what I've just said is nothing totally new. It's already a real world application in several websites. Twitter is just an example, where they don't need you to explicitly tell them what your features are. They can automatically deduce your pseudo features, and in some cases that might be more accurate. Let me also take a huge leap of faith and make a huge prediction. And not only that, you can intercompare, say, words with each other. I think later we'll be able to map abstract ideas to objects. Say, for example, take these words: youth, religious, and influential. And say your question is, who is the best person that, you know, encapsulate all these features, okay? I just gave an example. Let's say it's Ahmed Shigeri, okay? So, but this is me reading the words and coming up with an example. But we are very close in doing this automatically by pseudo feature extraction. You can, if say your goal is to convey a message, a certain message, you're a company, you're a university, any organization, and you have say certain motto or messages that you want to convey, and who's the best person that might be a good representative for this company. It's no longer a subjective measure. Later on, it could be very objective. You can just rank people according to the measures you've set. Now, if you, and you can do also the opposite. Say, take a person like Neil deGrasse Tyson again, and what are the best, you know, words that describe this person? You might. I just came up with these words. This is not real analysis. So his scientists are obviously charismatic, cool. So you can. There's a famous idiom in English. Apple and oranges, where whenever you cannot compare two things, they would normally say to you, it's like comparing apple and oranges, as they're non-comparable. I hope you're convinced by now that they're very comparable if you if you extract their pseudo features. Obviously, they're not comparable using their features, although they're very close. I don't know why they keep using orange and apples. They're fruits. I mean, that's one obvious thing. But I think in the future we'll be able to also compare apple and orange. If that makes any sense. So that concludes my talk, basically. Thank you very much for your attention, and I'll be happy to answer any questions either via audio or via text. Thank you very much again for listening.